All right, we are getting ready for the next talk. Paul Großkopf will speak about the Hopf category of Frobenius algebras. Please go ahead.
Yeah, thank you very much for the introduction. I also want to thank the organizers for giving me the opportunity to speak here at this conference. And what I'm going to speak about is the Hopf category of Frobenius algebras. And this is joint work with my supervisor in DLB, Jos. This is still very much work in progress. So what I try to do today is give you a rough idea what our ideas are, but there's going to be at least two nice results stating that we can organize Frobenius algebras in a Hopf category. So our motivation for this comes from TQFTs. So topological quantum field theories come from physics, but there's a really nice and neat description in category theory due to Atiyah. And let me state that for you. So TQFT is a functor, and it's usually denoted by some Z. From the category of n cobordisms to some other category C, and both of them are endowed with a symmetric monoidal structure. So we also ask the functor to be symmetric monoidal. This category here on the right-hand side is quite variable. We use different notions here. But you can imagine that just to be the category of vector spaces with usual tensor product. Instead of redefining what this NCOB is, I want to give you a few examples to save some time. So if you look at n equals 2, we want to describe the category of n of two cobordisms. So the boundaries, the objects in this category are the boundary components, and these are one-dimensional compact manifolds. So these are just disjoint unit circles. And if I have an object here and an object here, the arrows I can build are just cobordisms between these. And since we're dealing with n equals 2, these are two-dimensional surfaces. I mean, to be precise, this n cobordism category often, like, there's variations. We look at oriented cobordisms, framed, but I don't want to be too precise because on what I'm talking, it's not going to matter too much. Maybe also let me give you the easiest example in dimension 1. So here we just have points with some orientation, and then the string diagrams between them. But we also can have closed strings that just come from the empty set, go to the end. So yes, so one of the questions we ask when we're dealing with TQFTs, we want to classify them. So we want to describe monoidal symmetric functors from NCOB to category C. Yeah, and there's little known, like we know it for dimension n, it's completely classified. These are just finite dimensional vector spaces. And for dimension 2, these are described by commutative Frobenius algebras. So for dimension 3 and 4, there's, to my knowledge, not a complete classification, but we have some examples. And I want to mention here Hopf algebras, and in dimension 4 we have Hopf categories, which is a multi-object generalization of a Hopf algebra. And maybe I mention here some authors. So the 4-dimensional is to Frankel and Crane, and the 3-dimensional is Jetta and Crane. So yeah, these are not complete classifications. These are just examples we have. Yeah, and like we want to understand the high dimensional versions because these are the ones that pop up in physics a lot. So now the main idea we were like starting to work on was just a really simple observation. Like if I take, for example, this cobordism and I embed it in a plane, and then I just cut it through. So maybe there's a color. No. If I just cut this through, then my circle will be split into 2 points here, and then the kind of the outline will be this. So I conveniently already drew this here. So by cutting this two-dimensional version, we get something that looks like a one-dimensional cobordism. So to formalize this a little bit, what we want to do is maybe take 2 cop, we create a functor to 1 cop, and by using one-dimensional TQT, we can therefore like compose this to generate it to the TQT. So yeah. So maybe let's look at this example. If you look what happens to the boundary components, to the objects. Here we have circles, and every circle is mapped to 2 points. One positive, one negative. And what the TQT does is assigns to this constellation a vector space dual tensor to vector space, which is isomorphic to an anamorphism space. And the anamorphism space can be described as a matrix algebra, which is a Frobenius algebra. So here's the moment I have to tell you that I lied to you. This construction doesn't really work because the matrix algebra necessarily is not really commutative. And the reason for that is that we have some switch map that we cannot really embed in a plane. But by making some modification, there will be probably a framework we can embed this construct. So this is a motivation. What was our next step is to look at endomorphisms, but not of finite dimensional vector spaces, but of Frobenius algebras. So let A be a Frobenius algebra. We want to have a notion, we want to describe either the endomorphism spaces, or more particularly, if we have 2, we want to describe the Hopf space. But it's pretty known that these are quite rigid. So dealing with Frobenius algebras, if I have a morphism, I know this is already invertible. So I can give you the inverse the other way around. So what happens to an object B? Maybe let's denote the co-multiplication of the unit in this Frobenius algebra by 1 and 2. Then I can explicitly write down what the inverse of this F is. So we take the co-unit in B of B times F of E1 and multiply this by 2. So if you've never seen that, just calculate it. It's an exercise you can easily do. So what does this yield is, if I have 2 non-isomorphic Frobenius algebras, then the homomorphism space is empty. And this is a if and only if condition. So the notion we have of Frobenius algebra morphism is not the one we can really work with because it doesn't give us too much. So we try to give a different notion of the Hopf space between 2 Frobenius algebras. And what we found that works in that case is measurings. So I want to talk about the measurings. And these measurings will turn out to be coalgebras, so measuring coalgebras. And this is due to Sweedler, who first defined it. And I also want to give you a little bit of motivation, what this does, and I'll like give you the definition straightforward. The way of thinking of these ordinary Homs is I can look at a Hom and I apply it to an A and I get something B. So I get some map phi that assigns some F, tensor A, it's just evaluating F of A. And for example, describing the property of multiplicativity, if I take two A and A bar, this is the same then F of A times F of A bar. And let me write it a little bit differently. This is F tensor F applied on A tensor A bar. And this already looks like a group-like element. So the idea is of putting a co-multiplication structure on these Hom spaces and then allowing different co-multiplications here, not just group-like elements. And this seems to be really fruitful. So the definition, you probably stated, I have two algebras A and B, but this works for arbitrary structures. Then a coalgebra C is called a measuring. We say measuring from A to B if there's a map phi that does simulate what I tried to explain to you, and there's conditions, of course, respecting the Frobenius structure. Maybe just let me give you one for multiplication. So sometimes we also write, instead of phi A as C tensor A, we just write C of A to kind of like make it more, think of the original example. So instead of C on a product just being C of A times C of A bar, we co-multiply the C and put one on the A, one on the A bar. Yeah, this is our definition we're working with. And now the question arises, like, this is just one. I just gave a definition for one. Which one do we use? And luckily, there's a universal one. So this theorem is due to Agor, Gordienko. I hope I don't mix up the name. And Verkrisse. And it states that there is a universal measuring coalgebra. And universal in which sense? If I have any, maybe let's put it P coalgebra, and I can measure from A to B, then I have the universal one, then this always factors. So in particular, what they also proved, so they proved it in a really general setting for A and B to be arbitrary omega algebras. So omega algebras are just a generalization of algebras, coalgebras with arbitrary parity and those arbitrary rules, how they interact with each other. But what they proved is in the general case that this C will always be a bi-algebra. So yes. So what we were able now to prove was that if we go to the specific case where A and B are Frobenius algebras, we can create an antipode and therefore get a Hopf category. So let me denote this by Frobenius star. This is the category of Frobenius algebras with the arrows just being the the measurings. Is a Hopf category. So if you never heard this explicitly, this means this is enriched in coalgebras, and I get a family of maps from the co-measuring from the measuring from A to B to the measuring of B to A. This is an anti-coalgebra map. And this satisfies the antipode condition as in the one object case, but you always have to like make sure that you're using the right direction. So yeah, this is something we were able to show and how does the proof work. It's basically already in the blackboard. Instead of looking at F's here, I just put elementaries like C's from the co-measuring, and then the proof works the same. There's some difficulties looking at the direction in which way the arrow goes, but basically this is just combining something that works for Frobenius morphisms and lifting it to this higher extended notion of morphism. So yes, since I already misspoke a little bit, there's a dual theorem where you do all this, but with the notion of the co-measuring, and then you can also show that this is enriched. This can be organized in a Hopf category. So where we have local algebra structures and a global co-measuring. So yes, this is the result we have. And now we want to go back. So we have a connection between the case of Frobenius algebra and Hopf algebras. Yeah, maybe in that case, if we look at A equals to B, what it means to be a Hopf category just means in that case that for these objects, this is a Hopf algebra. So we have this connection between the two-dimensional case and the three-dimensional case, but we don't know yet how to connect that back to the cobordism side. And that would be the next steps we try to find, and also find the right framework to work in, because these TQFTs, they have very different notions on how to look at them. And it's kind of like, usually you start with the things you want to show and then find the right properties, and we kind of like have now this result and we want to take it back. If I'm doing good on time. Okay, then I want to maybe talk about some examples. So yeah, I already deleted it right now, but the first question you could ask is, does this notion give us more than we already have? So do I find new interesting functions from A to B that are not in the endomorphisms? The other question is like, we still don't know if this is 0, if A is not equal to B. So the way it works to generate more examples, at least the way I'm working, is this 3-step program. So I pick 2 algebras, A and B, and I can calculate this is the co-measuring algebra. So the dual version of what I was telling you. I'm working with that because that has a really nice, neat description of generators and relations, which the measuring algebra doesn't have really. There's a theorem that states if you dualize this one, where I'm using the Sweetler dual here, we get back to the measuring case. And then I interpret this, the one I just calculated. So if we're lucky and this is finite dimensional, we don't really need to worry about this Wheeler dual here. We can just take a normal dual. So and now I'm like a little computer and just taking two algebras, calculating, seeing what's happening. And there's just a limit on how much you can do by hand. And I guess at some point you either need to use a computer to generate more examples, or we find a more structural approach. So let me take 3 examples and 3 non-examples. So I first looked at group algebras because they're the easy ones you can describe. Because the computation gets quite intense. Like I think it's squared in a number of elements. So if I just take the base field, nothing really interesting happens. If I take the first non-trivial example, the group algebra over the cyclic group with 2 elements, I get something that looks really similar, but I want to write it like this. Okay, the polynomial in X, and I factor out X per minus 1. And the third example, which is the next less complicated one, is already a little bit more interesting. Here I have 2 copies in a direct product. So to answer the first question, is there more in these endomorphisms? Because these are all endomorphism spaces, basically. We get more functions here. We have 2 generators, the one and the X. And these are, if you look at 1 plus X, this is the identity, but the 2 parts separately already describe some appropriate measurings. In this case, this is much more interesting. So we have 6 different generators. They all do something different, and we still don't really know why this appears and why it's like this. And maybe in these 2 cases, maybe the characteristic of our field is actually we get a derivation. And the same we can prove if the characteristic in the third case. And maybe some non-examples. I think I can prove that if I look at group algebras of 2 different groups, G and H, this is 0 if and only if they don't have the same number of elements, which is a step closer to say, oh, they need to be isomorphic, but this is the state we are right now, so non-examples. The next class I was looking at were matrix algebras. I can prove something similar here. If I have the matrix algebra dimension n and m, then these need to be different. And I also can show that if I take 1 matrix and 1 group algebra, there's also none. So we still have a lot of examples where this is still 0. So yeah, I would be happy if someone has more insight into Frobenius algebras, even on normal morphisms. Because there's still like a lot of open questions popping up since we. So I think I conclude here, and thanks for your attention.
Thank you. Thank you very much. Do we have questions for Paul? Yep.
In the example 2, the so you did put a circle for the dual. You mean there the rational dual as a Hopf algebra, or
The Sweetler dual. The Sweetler dual. So if I understand correctly, it's you take the full dual, and then you only restrict to the ones that the co-multiplication doesn't have. So the co-multiplication still can be represented in finite
this
sums.
is the rational dual? Yes,
Oh, okay.
that's what I expected.
Not to speak into the terminology.
Any other question in the audience? It's not the case, but we have an online question. Please go ahead.
Hi, thank you for your nice talk. I have, sorry, you can see. I missed something in your talk. Could you please tell me? So when you wrote the claim that Frob is a Hopf category, so first of all, how is it defined? What is Frob?
What is what? Sorry, I didn't.
You know, Frob with star was the notation for what you say it is a Hopf category. I missed, yes. What? How is it described? I mean, what is it? What are zero cells? What is it?
The objects are Frobenius. Sorry?
Yeah, what does it contain? What is it?
The objects are Frobenius algebras.
Yeah.
Arrows between are these measurings.
It is a one cat. Measurings are.
It's one category, yes. Yes.
Yeah.
I mean, maybe if we, sorry.
It is enriched in just co-alg, or I mean, how do measurings pop up if you are only enriched over co-algebra? I mean, I'm missing something.
So the definition of a Hopf category is enriched over co-algebras and having antipodes. So, I mean, already by the theorem I stated, we can also say this is enriched in bialgebras. No.
Okay, I understood something there that you said that these are measurings, this CAB, or are they only coalgebra maps, this CAB?
No, they're the measurings, as in the definition. I mean, I left out a lot of the conditions. They, the elements, how they work on the element A.
Okay. Yeah, I saw it's something I was missing. Okay, thank you.
Okay, thank you.
All right, so I think it's time to say thank you again for your talk.